Welcome to our comprehensive guide on climate literacy. In this video, we'll break down the essential concepts that help us understand how Earth's climate system works, why it's changing, and what evidence supports these changes. Whether you're a student, educator, or simply curious, this journey will equip you with the knowledge to interpret climate science and its real-world impacts. We'll start with the sun's influence, move through atmospheric processes, explore the carbon cycle, and end with how scientists detect and attribute climate change. Let's begin by exploring the fundamental drivers of Earth's climate. Sun is the primary source of energy for our planet, but its output isn't perfectly constant. Over an 11-year sunspot cycle, the sun's energy output varies slightly, but this variation is too small to explain recent rapid warming. Historical periods like the Maunder Minimum saw reduced solar output and cooler climates, such as the Little Ice Age in Europe. However, satellite data since 1978 show no upward trend in solar output, even as Earth's surface temperatures have risen. This points to other factors driving modern warming. Additionally, Earth's orbit and tilt change slowly over tens of thousands of years, packing the ice ages through cycles called Milankovitch cycles. These cycles alter how sunlight is distributed, but their effects are too slow and currently in a cooling phase, not responsible for today's rapid warming. During the last glacial maximum about 21,000 years ago, Earth was much colder with vast ice sheets covering large parts of the continents. While orbital cycles initiated these ice ages, the full swings in temperature were amplified by feedbacks. Growing ice sheets reflected more sunlight, causing further cooling, and colder oceans absorbed more CO2, lowering atmospheric levels and reinforcing the chill. These feedbacks show how interconnected Earth's systems are. Today, however, these slow cycles can't explain the rapid warming we observe, which is happening much faster than any natural cycle in the recent geologic past. Understanding how energy moves through the climate system starts with radiation laws. The sun, being much hotter than Earth, emits mostly visible and ultraviolet light while Earth emits infrared radiation. The Stefan-Boltzmann law tells us that hotter objects emit more energy, and Wien's law explains why the sun's peak emission is in visible light while Earth is in the infrared. These basic physical laws underpin how energy is absorbed, emitted, and transferred in our atmosphere, setting the stage for the greenhouse effect. Not all gases in our atmosphere interact with radiation the same way. Nitrogen and oxygen, which make up most of the air, don't absorb infrared radiation. Greenhouse gases like water vapor, carbon dioxide, methane, and ozone, however, absorb and emit infrared energy in specific bands. This selective absorption is why greenhouse gases are so important. They trap heat that would otherwise escape to space. Some gases, like ozone, also absorb harmful ultraviolet light, protecting life on Earth. The unique properties of each gas shape how energy moves through the atmosphere. Greenhouse effect is central to Earth's climate. Without an atmosphere, Earth would be a frozen world, radiating heat directly to space. Thanks to greenhouse gases, some of the infrared energy emitted by the surface is absorbed and re-radiated back down, warming the planet by about 33 degrees C above what it would otherwise be. This effect keeps Earth habitable. When greenhouse gas concentrations increase, the effective radiating level rises to a colder altitude, causing an energy imbalance. More energy comes in than goes out, so the planet warms until balance is restored. Think of greenhouse gases as a blanket around the planet. Adding more CO2 is like adding another layer to that blanket. Initially, this slows the loss of heat, creating an energy imbalance. The Earth then warms until it can again radiate as much energy as it receives from the sun. This analogy helps explain why increasing greenhouse gases inevitably leads to global warming. It also clarifies why the stratosphere cools as the lower atmosphere warms, a unique fingerprint of greenhouse gas-driven change. Carbon moves constantly among the atmosphere, oceans, biosphere, and rocks. The atmosphere holds only a tiny fraction of Earth's carbon, while the oceans and rocks store much more. Plants absorb CO2 through photosynthesis, releasing oxygen, while respiration by plants and animals returns CO2 to the air. Oceans absorb and release CO2, with cold waters taking up more. This dynamic cycling keeps atmospheric CO2 in balance, unless disrupted by human activity. Photosynthesis and respiration are the engines of the fast carbon cycle. Plants taking CO2 and sunlight to build organic matter, releasing oxygen. Animals and microbes break down this organic matter, releasing CO2 and water. These processes are massive in scale and were balanced for thousands of years before humans began altering the system. Today, human activities have tipped the balance, adding more CO2 than natural processes can remove. The ocean is a giant carbon sink, absorbing about a quarter of human CO2 emissions. CO2 dissolves in surface waters, forming bicarbonate and carbonate ions. Cold water absorbs more CO2 while warming or turbulence can release it. Because the deep ocean mixes slowly, it takes centuries for atmospheric CO2 changes to fully equilibrate with the ocean. This slow mixing means the ocean can buffer changes, but only up to a point. The sunlit surface ocean, tiny organisms called phytoplankton use CO2 for photosynthesis, forming the base of the marine food web. When these organisms die or are eaten, organic matter sinks into the deep ocean where it decays and releases CO2. This process, known as the biological pump, helps store carbon in the deep ocean for centuries, keeping atmospheric CO2 lower than it would otherwise be. Over millions of years, the geologic carbon cycle stabilizes atmospheric CO2. Weathering of rocks on land consumes CO2, delivering bicarbonate to the oceans. Marine organisms form shells from this carbon, which eventually becomes limestone. Tectonic processes can later release this carbon back into the atmosphere through volcanic eruptions. This slow cycle acts as a long-term thermostat for Earth's climate, balancing CO2 over geologic timescale. Humans have dramatically altered the carbon cycle, mainly by burning fossil fuels and changing land use. Each year we emit about 10 billion tons of carbon from fossil fuels and another billion from land use changes like deforestation. These activities transfer carbon from long-term storage in rocks and forests into the atmosphere as CO2, much faster than natural processes can remove it. This rapid input is the main driver of rising atmospheric CO2. Not all the CO2 we emit stays in the atmosphere. About 45% remains aloft while the rest is absorbed by oceans and land plants. But these natural sinks can't keep up with the rapid flow from human activities. Imagine the atmosphere as a bathtub. The faucet emissions is running faster than the drain natural sinks, so the water level CO2 keeps rising. This is why atmospheric CO2 has climbed from 280 ppm before the industrial era to over 420 ppm today. Ocean's uptake of CO2 helps slow climate change, but it comes at a cost: ocean acidification. Dissolved CO2 forms carbonic acid, lowering the ocean's pH. Since industrial times, surface ocean pH has dropped from about 8.2 to 8.1, a 30% increase in acidity. This harms marine life, especially organisms that build shells or skeletons from calcium carbonate, like corals and some plankton. Ocean acidification is a major consequence of rising CO2. Terrestrial ecosystems, especially forests, currently absorb a significant share of CO2 emissions. Forest regrowth and CO2 fertilization help, but this sink may not last forever. Warming, nutrient shortages, and ecosystem saturation could reduce land uptake in the future. In high-latitude regions, permafrost soils store vast amounts of carbon, but as they thaw, decomposition releases CO2 and methane, potentially accelerating climate change. Significant portion of the CO2 we emit stays in the atmosphere for thousands of years. Even if emissions stopped today, CO2 would only decline slowly as it's gradually removed by the ocean and rock weathering. This means the climate changes we set in motion, like warming and sea level rise, will persist for generations. The slow removal of CO2 underscores the urgency of reducing emissions now to limit long-term impacts. Methane CH4 is a powerful greenhouse gas, trapping much more heat per molecule than CO2, though it's less abundant. Its sources include wetlands, agriculture, especially rice paddies and livestock, landfills, and fossil fuel extraction. Methane's atmospheric lifetime is about 12 years, short compared to CO2, but its warming effect is intense. Reducing methane emissions can yield relatively quick climate benefits. Nitrous oxide, N2O, is another potent greenhouse gas, with a long atmospheric lifetime and high global warming potential. It's released mainly from agricultural soils, fertilizers, and livestock manure. Tropospheric ozone O3, formed by reactions of pollutants in sunlight, is both a greenhouse gas and a harmful air pollutant. While stratospheric ozone protects us from UV radiation, ozone near the surface contributes to warming and health risks. Chlorofluorocarbons, CFCs, and related halocarbons are human-made gases once widely used in refrigeration and aerosols. They are extremely potent greenhouse gases and also destroy stratospheric ozone. Thanks to international agreements like the Montreal Protocol, CFCs are being phased out, but their replacements like HFCs are still rising. These gases, though present in tiny amounts, have a significant impact on climate due to their high global warming potential. Agriculture is a major source of non-CO2 greenhouse gases. Livestock, especially cattle, produce methane through digestion, while rice paddies and manure management add more. Fertilized soils emit nitrous oxide. Altogether, livestock supply chains account for about 15% of global greenhouse gas emissions. Changes in diet and improved agricultural practices can significantly reduce these emissions. Water vapor is the most abundant greenhouse gas, responsible for about half of the natural greenhouse effect. However, its concentration depends on temperature. Warmer air holds more moisture. This makes water vapor feedback, not a direct driver. As the climate warms, more water vapor enters the atmosphere, amplifying the initial warming. This positive feedback roughly doubles the warming caused by CO2 alone. Clouds play a dual role in Earth's climate. They reflect sunlight, cooling the planet, but also trap infrared radiation, warming it. High, thin clouds tend to warm, while low, thick clouds cool. Overall, clouds currently have a slight net cooling effect, but how they will change as the planet warms is the biggest uncertainty in climate projections. Changes in cloud cover or type could either amplify or dampen future warming. Climate sensitivity measures how much Earth's temperature will rise if CO2 doubles. Without feedbacks, a doubling would cause about 1–2 degrees C warming, but with feedbacks like water vapor and clouds, the likely range is 2–4–5 degrees C, with a best estimate around 3 degrees C. This sensitivity explains why even small increases in greenhouse gases can have large effects on global climate. Aerosols are tiny particles in the atmosphere from sources like dust, sea salt, volcanoes, and human pollution. They scatter and absorb sunlight, with most human-made aerosols like sulfates reflecting sunlight and cooling the planet. This cooling has partly masked global warming, especially during the mid-20th century when industrial pollution was high. However, as air quality improves, this masking effect is reduced. Aerosols also affect clouds. More aerosols mean more smaller cloud droplets, making clouds brighter and longer lasting. This increases cloud reflectivity and enhances the cooling effect. These indirect effects are harder to measure than direct aerosol cooling but are significant. Overall, aerosols have exerted a net cooling influence, offsetting some greenhouse warming over the past century. Like greenhouse gases, aerosols remain in the atmosphere for only days to weeks. They are quickly removed by rain and gravity, so their concentrations are highest near sources like cities and industrial regions. Major volcanic eruptions can inject aerosols into the stratosphere, causing global cooling for a year or two. This short lifetime means aerosols have strong regional effects but don't accumulate globally like CO2. Efforts to reduce air pollution by cutting sulfate and soot emissions improve health, but also remove some of the cooling influence of aerosols. This can lead to a slight increase in warming unless greenhouse gas emissions are reduced at the same time. Cleaner air is a win for health and ecosystems, but it highlights the need to tackle greenhouse gases directly to address climate change. Cooling effect of sulfate aerosols has inspired ideas for solar geoengineering, deliberately injecting particles into the stratosphere to reflect sunlight and cool the planet. While this could offset some warming, it wouldn't address other problems like ocean acidification and carries risks such as altering rainfall patterns. Geoengineering would require ongoing maintenance, and stopping it suddenly could cause rapid warming. Oceans are Earth's largest heat reservoir, absorbing over 90% of the excess heat from greenhouse warming. Their vast volume and high heat capacity mean they warm slowly, buffering surface temperature changes. However, this heat uptake also causes thermal expansion, which is the leading contributor to sea level rise so far. The ocean's role as a heat buffer is crucial in moderating the pace of climate change. Global ocean features a density-driven overturning circulation, often called the global conveyor belt or thermohaline circulation. At high latitudes, cold, salty water sinks to the deep ocean, driving a slow but powerful flow that redistributes heat and nutrients around the globe. This circulation helps keep Western Europe mild and transports carbon and nutrients. Changes in this system can have major impacts on regional and global climate. Paleoclimate records show that the thermohaline circulation has changed in the past, sometimes abruptly. For example, during the Younger Dryas, a sudden influx of freshwater likely weakened North Atlantic deepwater formation, causing regional cooling. Today, melting Greenland ice and increased rainfall could slow this circulation. While a complete collapse is unlikely this century, a slowdown could still have significant climate effects. Surface ocean down to about 100 meters is well mixed and exchanges heat with the atmosphere. Below this, the deep ocean remains cold and isolated, except where water sinks at high latitudes. Most heat from global warming accumulates in the upper ocean first, with deeper layers warming much more slowly. This strong stratification means the ocean can absorb heat without a uniform temperature rise. Ocean acts as a global heat conveyor and buffer, moderating the rate of climate change. It also absorbs about a quarter of CO2 emissions, helping to slow atmospheric buildup. Ocean currents distribute heat and influence regional climates such as El Niño and La Niña events. Changes in ocean circulation or heat content are both symptoms of and contributors to climate change. Understand past climates. Scientists use proxy data, natural recorders like tree rings, ice cores, sediment layers, and corals. Each proxy responds to specific climate variables and covers different time spans. For example, tree rings reveal annual temperature or rainfall, while ice cores preserve ancient air bubbles and isotopes that indicate past temperatures and greenhouse gas levels. These records extend our knowledge far beyond the era of direct measurement. Tree rings provide annual records of climate, with ring width and density reflecting growing conditions. Ice cores drilled from polar ice sheets preserve layers of snow and air bubbles going back hundreds of thousands of years. The isotopic composition of ice reveals past temperatures, while trapped gases show historical greenhouse gas concentrations. Together, these proxies offer a detailed view of climate variability over centuries to millennia. Ocean sediment cores contain layers of microfossils whose chemistry reflects past ocean temperatures and ice volume. Coral cores, with their growth bands and chemical signatures, record sea surface temperatures and salinity in tropical regions. These proxies, along with others like cave stalagmites and pollen and sediments, help reconstruct climate over thousands to millions of years, each with its own strengths and limitations. Different proxies are suited to different time scales and regions. For the last 2,000 years, scientists use a mix of tree rings, corals, ice cores, and historical documents. For longer periods, ice cores and ocean sediments are primary. Using multiple proxies increases confidence in reconstructions, as agreement among different records strengthens the evidence for past climate changes. Earth's climate naturally fluctuates on yearly to multidecadal scales due to internal variability. Major modes include the El Niño, Southern Oscillation ENSO, which shifts ocean temperatures and global weather patterns every few years. Other oscillations, like the Pacific Decadal Oscillation and Atlantic Multidecadal Oscillation, modulate regional climates over decades. These patterns can temporarily enhance or dampen global warming, but do not explain the long-term trend. Niño events bring warmer ocean waters to the eastern Pacific, shifting rainfall and raising global temperatures, while La Niña does the opposite. Decadal oscillations like the PDO and AMO affect climate over longer periods, influencing droughts, hurricanes, and regional weather. These oscillations cause ups and downs in global temperature trends but average out over time, leaving the long-term warming trend driven by greenhouse gases. It's important to distinguish between short-term climate variability and long-term trends. Internal oscillations can cause temporary warming or cooling, but only greenhouse gas increases can explain the persistent, global rise in temperature over the past century. Scientists use statistical methods and long-term records to separate the human-driven trend from natural fluctuations. Holocene, our current interglacial period, has been relatively stable compared to the ice ages. Over the last 1,000 years, proxy records reveal modest variability, with periods like the medieval warm period and Little Ice Age. However, recent warming since the industrial era is much larger and faster than any changes in the past millennium, as shown by the famous hockey stick graph. Hockey stick graph, first published in 1999, shows a long period of stable or gently cooling temperatures followed by a sharp rise in the 20th century. Multiple independent studies using different data and methods have confirmed this pattern. The focus on a single study by skeptics is misplaced. Replication by many teams has firmly established that recent warming is unprecedented in at least the last 1,000 years. Since the late 19th century, direct measurements show global surface temperatures have risen by about 1 degrees C. Warming is global but uneven, with land and the Arctic warming fastest. Sea level has risen about 20 cm, mainly from ocean expansion and melting glaciers. The cryosphere is shrinking, with less Arctic sea ice, retreating glaciers, and thawing permafrost. These changes are unprecedented in the context of the last few thousand years. Scientists distinguish between detecting climate change and attributing its causes. Detection means showing that observed changes are statistically significant and not due to natural variability alone. Attribution involves identifying the causes, mainly greenhouse gas increases. Multiple lines of evidence, including climate models, satellite data, and physical fingerprints like stratospheric cooling, confirm that recent warming is overwhelmingly due to human activity. This scientific consensus drives global efforts to reduce greenhouse gas emissions and address climate change.